I would like warmly welcome you to my lecture with the title Structure Design Criteria for Road Bridges made of UHPC large prefabricated parts, approaches to possible CO2 savings potential in bridge construction. The entire civil engineering currently has a special responsibility in dealing with the climate crisis. My lecture now about the UHPC bridge family integral is a contribution to how we can improve girder bridges in terms of resources and CO2 savings compared to a current state of the art. Specifically, I would like to look at girder bridges in a medium span range from 30 to 80 meters and based on a comparative calculation of a 170-meter long bridge to bring you closer to the advantages of the UHPC bridges in terms of resource and CO2 savings compared to conventional reinforcement concrete girder bridges. It was previously the central task in the bridge designs to find an optimized balance between economic and aesthetics, and must now also be supplemented in the entire civil engineering by the concept of ecology. It is therefore important for the bridge designs to create a balance between economic, aesthetics, and ecology. This approach in the design of whole engineering structures and especially bridge designs is lived in our office through the so-called NEAR principle, which purpose of the holistic planning approach. NEAR principle means nature, ethics, and aesthetics are in a balanced relationship as value principles in every bridge design. Or we can say, in other words, only with a network balance between the environment, economy, and the state of the art can a technical, constructive building culture emerge. Before we deal with the UHPC bridge systems in detail, I would like to briefly discuss the state of the art in reinforced concrete girder bridges in the next 3 slides. The economical production of plain parallel girder bridges made of reinforced concrete for spans of 30 to 80 meters has resulted since the beginning of the 20th century primarily through the possibility of using pre-stressing and manufacturing process. The slenderness of the plain parallel girders is between 12 and 22, depending on the cross-section type and manufacturing process, as you can see on this on this table here. If large prefabricated parts are used over an entire field line, the maximum span are from 20 to 40 meters. The field-by-field stem serves as a preferred manufacturing process. Historically, at the beginning of the 20th century, the plain parallel girder was used at a much later point in time than hinged girder. The hinged girder, in turn of the development of frame, and this in turn development of arch. If you want to increase the efficiency of the plain parallel girder, tension stiffening systems are used in bridge construction, as you can see on this slide. The temporary high point of increase in performance is achieved by cable stayed bridge. Concrete sail bridge, such as Ganter Bridge, designed by Professor Mann in the picture here, are statically the inversion of the hinged girder. The slenderness is 10 to 12. The mentioned slenderness of both systems, the concrete sail and the plain parallel girder bridge, are also used in the design of UHPC system, as we will see later. Slide 6 shows an overview of the design options for the UHPC integral bridge family for small to large bridges. The term bridge family subsumes different technical development stages from the simple single span girder, UHPC 125 and 225, as shown here in figure A, the frame UHPC 325, to the continuous girder UHPC 500, as you can see here in figure C. The resource efficiency required at the beginning of my lecture, or the introduction of ecology in bridge construction, is achieved by optimizing the material, structure, and manufacture. The material is denoted ultra high performance concrete, named UHPC, with steel fiber and steel bar reinforcement. With increasing strength of the material, the energy consumption in global warming potential in relation to the compressive strength decreases. To ensure sufficient post-crack resistance, an amount of steel fiber greater than 1.5 volume % is used. Steel bar is specifically used only in the highly stressed area of the load path. The cross-sectional shape of all types of the bridges, you can see here, is a trough shape. The structural efficiency through folding, topology optimization, and integration is explained in the next 3 slides. The loading of the UHPC trough plates take place as a shell, which means the designs are surface active support systems. The structural efficiency is further increased by 2 folding steps, alpha 1 and alpha 2, and it based on a vertically element. You can see the effect of the folding using the example of the Paulifort Bridge, as you can see here in the picture. That was been built in 2015 in Austria. If you drive over the viewer, can feel the dynamics of the bridge and represents an added value. On this slide, you can see the topology optimization into 2 steps. On the left side, here, you can see triangular opening geometries, like here, that are specifically used in the less stressed area of UHPC plate. lighting elements integrated in the openings are additional design elements. On the right side here of this slide, you can see the arrangement of ribs from 150 to 225 millimeter thickness for the different type of applications, started from UHPC 225 to UHPC 500. The ribs are arranged along the load path of the UHPC plate and can receive also pre-stressing elements. An additional optimization of the structural efficiency is achieved through an integration process. The monolithic construction is directly connected with the increase in lifetime or with the increase of durability of the bridge construction. The implementation of the integration in the UHPC bridge family integral takes place through decoupling. In order to minimize enable constraints from load-dependent effects, even for long bridges, the deck slab system 2 is structurally separated from the longitudinal support main support system, system 1. Both systems, system 1 and system 2, form independent decoupled integral system in a longitudinal direction. With using white cement, the light coloring of the UHPC trout plates also leads to lower temperature loads. This slide shows the structural design criteria of the UHPC trough plates for the type UHPC 500. It can be seen that the slenderness 8 to 10 over the supports corresponds to that of the concrete sail bridges, and the slenderness 15 in the middle and or border field corresponds to that of plain parallel girder bridges, as we saw on the slide 4. With this structural design criteria for a UHPC bridge, a 170 long 4-span road bridge with spans of 35, 50, 50 and 35 meter, a comparative calculation with a pre-stressed concrete bridge was carried out with regard to masses and CO2 savings. So you can see on the next next slide. On the left, the cross section of the two 10.5 wide comparison bridge are shown. The mass saving of the comparison of the UHPC bridge to pre-stressed concrete bridge is of approximately 40%. The saving of the comparison from cradle to gate is approximately 15%. If the performance of the steel fibers, which mean a high level of energy input into the UHPC matrix, can be improved, CO2 savings of up to 22% would be possible. With this slide, I would like to come to my summary of my lecture and the advantage of using UHPC bridges. If UHPC bridges are planned appropriate to the material, it is possible to achieve enormous mass savings as well as CO2 savings. A prerequisite for this is the use of the high-performance material UHPC as a surface active support system. With the introduction of the structural ecological efficiency factor named Big Star, an assessment of bridge design with regard to structural and ecological efficiency could be given in the future. Civil engineers should consider not only economic and aesthetics, but also ecological efficiency of the design. If we use the material UHPC appropriately to the material, it's particularly suitable to the monolithic construction without bearings and transition joints, and if details are also appropriately designed to the material, this enables a long lifetime for the construction. As far as the design and aesthetics of a UHPC bridge are concerned, I'm of the opinion that the material UHPC can make the line of forces even more visible, and thus offers ideal conditions for beautiful constructions. The final slide shows an already built project of a UHPC frame bridge, as you see before, the Paulifort Bridge, as well as a possible uses for UHPC continuous girder bridge with high ecological efficiency, maybe for the future. I thank you for your attention and hope I have inspired you with my suggestions for building with UHPC. Thank you very much.